Okay, right. It's been about 18 months since I gave any talk or lecture on Kryptos, like I did in the maths class at the University of Queensland for coding in cryptography, but maybe it's time for another presentation. So here we are again. I'd like to start with some quotes. Here's a technical one from Alan Turing from a paper written in 1941 or 42. That paper wasn't declassified until 2012 to 2015. So he talks about statistics, or the theory of probability, and how it can be used to determine what kind of cipher is being used for a particular ciphertext. So with Kryptos K4, people spend a lot of time trying to diagnose what kind of cipher it is, and certainly probability theory and Monte Carlo methods can really help with that. Okay, and here's another quote from Nick Patterson, who used to be at GCHQ. The quote is, it helps to have a well-honed instinct about whether you're seeing a pattern, or whether the pattern you think you're seeing actually turns out to be complete nonsense. Or in other words, if you're seeing simple random fluctuation or a smoking gun. And in case I'm not being clear in this presentation, I'd like to quote Mary D'Imperio and say, if we understand what we're doing, or if I understand what I'm talking about, I should be able to express it clearly with a minimum of jargon, like, for example, the word cryptodiagnosis. Okay. So one technique we can use for cryptodiagnosis is we can look at statistics, like the number of repeated n-grams. That's the number of repeated sequences of n letters, and decide how unusual the numbers are with respect to English, with respect to random text, random letters, and with respect to the ciphertext itself. Now, the first two, looking at statistics with respect to English and random letters, we're going to see that this has been done for lots of known ciphers, but the third one isn't done very often. It's a bit like a dragon eating its tail in some ways, but I think you'll see that it's quite helpful with some kinds of ciphers. So, Monte Carlo simulation, that's doing lots of random shuffles of the ciphertext and looking at the statistics. So, as Jim Galogli has said, this is fraught with peril, but also the idea underlies Turing's paper on the statistics of repetitions, if you want to take a look at that. So we take out all the question marks and all the spaces, and we'll just say n2, 3, 4, and 5 for the number of repeated n-grams of length 2, 3, 4, 5, and so on. If you were to look at the K1 ciphertext of 63 letters, say you know where the word divisions are, sorry, the ciphertext divisions, then you'll see VJYQT is repeated twice in the 63 letters, and you have to decide if that's a coincidence or not. In fact, it corresponds to NCEOF being repeated in the plain text. So once you know the plain text, you can see that wasn't a coincidence. So we'll look at that in a bit more detail. You see the same thing in the K2 ciphertext. GWHKK corresponds to SIBLE, and VPD corresponds to 8. And in the plain text, you also see the 8-letter sequence location being repeated. K3 ciphertext, maybe you don't see that so much because it's transposition, but certainly in the plain text, you have from the 7-letter sequence being repeated in 336 letters. In the K4 ciphertext, you have 10 different bigrams occurring more than once. And in the K4 plaintext, you would expect to see between 12 and 27 repeated bigrams or 2 grams, and between 2 and 24 repeated trigrams. If you were to look at the first and 99th percentile of English text, say taking the King James Version of the Bible. So as I was saying, people have looked at the statistics of ciphertext that comes from lots of different American Cryptogram Association cipher types. So if you go to this Bion's Gadget homepage, he's got a reference statistics homepage, and he assumes that all of these statistics are normally distributed. So that's why you've got, say here, 63 plus or minus 5. It means the mean is 63 for the index of coincidence, and the standard deviation is 5. So if you go too far away from 63, then you start saying, well, it's unlikely to be plain English text. And similarly, let's go for the 4-square cipher. If you get too far away from 0.048 for your index of coincidence, that's an argument against the ciphertext being 4-square output. But of course, Bion's goal is to distinguish between known cipher types. So the reason he doesn't consider repeated n-gram counts directly for n greater than 2 is that that's his goal. So when you see here DIC and EDI, that's the digraphic and index of coincidence and the digraphic index of coincidence at the even offsets. And for example, like 6x6 Playfair, you see that they're quite different there. But he doesn't consider n greater than 2 because he's not trying to do cryptodiagnosis between unknown systems. Okay, but that's what we're going to have to try to do with K4. So let's just take a quick look at how unusual these patterns are. We'll do Monte Carlo simulation. We'll maybe not assume that the values are normally distributed. And I think part of the reason that Bion and Alan Turing and all the people in the past don't generally do this is that it's quite computationally intensive to look at whether these NI values are unusual versus shuffles of the ciphertext itself. Okay, so we won't assume that the values are normally distributed. The statistics are going to differ based on the input length. So we're going to have to look at K1, 2, 3, 4 differently. And to look at what it's like against English text, we'll just use the King James Version of the Bible. So K1 is a 63 character text. And if you were to look at the Bible, you'd expect about 10 repeated bigrams in a 63 character text if it was plain English text. So in the K1 ciphertext, you see 6 repeated bigrams in the ciphertext and 11 in the plain text. So if you were to just consider random text, about 4% of random text have at least 6 repeated bigrams. But then if you were to just randomly shuffle the K1 ciphertext and compare it against itself, you'd see 3.2% of the random shuffles have at least 6 repeated bigrams. And then as you go into the 3 grams, the 4 grams, the 5 grams, it just gets extremely unlikely that what you're looking at is occurring by chance. So we have that, as I was saying, the VJYQT, 5 gram repeated twice, and only about 0.01% of the random shuffles of the ciphertext have that property. So I think at that point, you can quite confidently say that didn't occur by chance. So for some reason, that pattern is repeating itself, and that reason is that you're looking at polyalphabetic substitution there. And you see similar things for K2. It's a 369 character text. If you look at the trigrams, the 3 grams, you'd expect to see a mean of about 6 repeated trigrams, and what you find in K2, the original ciphertext, is you see 16 repeated trigrams, which is 4 standard deviations above the mean, about a 0.01% probability again. Okay. So for K3, well, Turing actually talks about this, that the statistics are different when you're just looking at shuffled plain text. And what you see is that there's, say, we count the repeated bigrams, trigrams, and quadgrams, but we don't see anything particularly unusual. For example, we have in the K3 ciphertext, we have 2 quadgram repeats, but that isn't actually all that unusual when we just look at random shuffles of the K3 ciphertext. But it's quite irrelevant here because we can just look at the index of coincidence to know that we're looking at a transposition cipher, and also the statistics of the letter frequencies. Okay, so here's an interesting article from Der Spiegel in May 1991, when Kryptos was being promoted in the English and German language media. So it's called Peinliche Zwiebel, which translates to the embarrassing onion in English. And what I find interesting about this is that it's the only time prior to Jim Gillogly on Crypt in 1999, June 1999, that Ed Scheidt was explicitly named as the consultant for Kryptos. If you look at all the other print media around that time, it's like an unidentified cryptographer, a retired CIA cryptography expert, that sort of thing. So ABC News in 1991 did an interview with Ed Scheidt. It's out there in B-roll transcripts, but I don't think it was ever used in the finished product, although I may not have seen all the TV output out there about Kryptos. But certainly this is one of the first times that this metaphor, the layers of an onion, was used. And what's interesting about that phrase is that it's been used many times by both Sanborn and Scheidt, which is curious. So the English translation is that the coding consists of many different layers. We could say that that's sections, or we could say it's techniques, each encrypted differently, which isn't really true for K1 and K2. The only difference between K1 and K2 is you've got to remember to take the question marks out for K2. But these different layers or different sections have to be peeled off one after the other like an onion. Now, is that just a reference to transposition and substitution being used in some order? It certainly reminds you of Ed Scheidt when he said in 2015 that he would consider the K4 encryption method to be more than one stage. So I think this is still in play, just a mix of transposition and substitution. Say, if you consider what happened in K1 and 2, we have 2 substitutions followed by transposition, or we could have something like double transposition followed by the polyalphabetic method you saw in K1 and K2. I think I would rule out the double quagmire 3 with Kryptos, or the standard alphabet and English keywords, because I've looked at the output of the that and check the statistics, and with the index of coincidence and chi-square stats, and I don't think that's a realistic possibility anymore. But it could be a simple transposition followed by polyalphabetic. I think the straightforward ideas like Hill cipher, Gromark, Playfair, 2 square, 4 square, all the variants, seriated Playfair, all of these things, I think we can consider them virtually eliminated. Scheidt has given hints that would seem to imply a Polybius square-based system, but just taking K4 ciphertext and not doing anything else first, I would say that the digraphic statistics and the index of coincidence aren't strong enough to indicate those. I think there are strong aesthetic arguments for using seriated Playfair. If you've got 98 characters, then it's 7 rows of seriated Playfair with 7. But again, you can't seem to do that in a simple way. So, having said that, like, my gut feeling is that transposition is involved, despite Sanborn's comments about there's a one-to-one correspondence between the ciphertext and the plain text. And he's used other metaphors like washing machine and turning, and so that leaves it as a possibility. And of course, there's also the analogous grill-based methods, and you can consider that to be transposition. Okay, and also obviously the index of coincidence is quite low. It's less than 1/26. You can choose that keyword to make the index of coincidence quite low, but it's hard to cover up those repeated n-gram statistics, like what we just saw in the analysis of K1 and K2. So getting on to K4, considering it is a 97 character text, if you had a 97 character text from the King James Bible, you'd expect to see about 18 repeated bigrams. If you were looking at random text, you'd expect to see about 6 repeated bigrams. But then if you shuffle K4, you look at random shuffles with your Monte Carlo method, you see about 5.5, standard deviation 2. About 3% of the shuffles have at least 10 repeated bigrams, and that's what you see in the K4 ciphertext. About 0.09% have at least 13, 0.02% have at least 14, and so on. So if you were to do a simple transposition, this is what I'm trying to say, and you saw at least 13 or 14 repeated bigrams, that would be quite suspicious. The only problem is, what is a simple transposition? And if I start to find myself doing lots of things and then taking the best result, that would be quite an invalid approach. So I want to convince myself that I am doing only very basic, simple transpositions that have some meaning in classical cryptography. Okay, so if you were to look at trigrams in that length of text, you'd expect to see about 9 repeated trigrams in plain text. If you were to look at random text, you get a mean of 0.25 and a standard deviation of 0.5, which really goes to show you shouldn't assume normality here. Look at shuffles of K4, you'd expect to see about 0.2 on average. But if you were to see, do your shuffle of K4 and then you were to see, say, 2 or 3 repeated trigrams, you'd start to say that was a bit suspicious. Okay. So the simplest K3 solution, I would say, is you write it as 337 characters or letters with a question mark at the end. and then you write out every 192nd character. So because the greatest common divisor of 192 and 337 is 1, you don't have any letters repeating itself. So you just get a sequence of letters just rearranged in the right order. So if we were to apply that same principle to the K4 ciphertext, if we were to start as 97 characters, or stick in a character somewhere, or leave one out, inspired by the 2006 hint that the K2 ciphertext needed an extra character, and then we go and take every X character, where the GCD of X and the ciphertext length was 1, then do we see any unusual patterns in those bigram counts or the trigram counts and so on? And just so we don't get confused, let's define an unusual event as the p-value is less than 0.01, so a 1% chance. Okay, so if we were to do that with 97 letters, at width 21 we find 13 repeated bigrams and 2 repeated trigrams. And if we were to do it at the in the reverse order, we'd see 14 repeated bigrams and 2 repeated trigrams. So this is just writing out the K4 ciphertext into a width 21 matrix going left to right, top to bottom. Now, we already said that you only see this in about 0.09% or 0.02% of random shuffles of K4 that you get these 13 or 14 repeated bigrams. But on the other hand, you considered a lot of different transpositions to get that, so it wasn't really valid. The question is, like, how wide do you consider these transpositions before you say it's just silly? I mean, if it's more than 42 characters wide, that seems to be the width of Sanborn's worksheets, so that would be silly. But if it's, you know, less than about 5 characters wide, that would also seem to be silly. Or even, you know, we could say anything between 7 and 21 is reasonable, but outside that range, it's not. But I would say that certainly seeing that many bigram and trigram repeats is unusual, and you don't see anything that unusual if you add or subtract characters. So I do indulge in self-delusion sometimes. Here's one example. If we were to do a double transposition using the keywords monarch and reckon or wrists. Monarch is certainly a sexy sounding keyword. If we go to the CIA Freedom of Information website, monarch is a code word that's apparently been used in the CIA context to smuggle B-26 bombers out of the US, which is interesting. So what have we got here? If we go up to this top matrix, you can start to see where I'm unwinding it. I write OBKR down this A column here, and then I've got QM, DO, DO here, and I write it down this column here with the C. And when I do that, I've got 21 repeated bigrams and 3 repeated trigrams. And if I were to do my Monte Carlo simulation, I would say the chances of that are about 7 billion to 1. But what I didn't tell you was how I found that. Basically, it was by going through all the different possible double transpositions, and so even if I did something simple like going through all the possible transpositions of width 7, we've got about 6,000 width 7 and less. 6,000 squares, 36 million. We're already getting up there saying, well, how I should evaluate this is dividing 7 billion by 36 million, getting about 200. it's 200 to 1. It's really not that unlikely because I've looked at millions of things. I still find it interesting and curious, which is why I shared it, but it shows you where the self-delusion comes in. So the question is, can we do something that's similar to width 21 transposition to work out what the correct first step was? And also, how would you identify what the correct first step was? How would you know you've got the correct intermediate ciphertext? So when you write the ciphertext at width 21 and you write out by columns, you see these repeated trigrams, LWA, QZT. That QZT is a byproduct of writing out the ciphertext at a width 7, which I'll talk about soon. You see a lot of doubled letters offset at the width 7 multiples. So one idea is that the QZT reflects underlying repeated plain text. So in the K1, 2, and 3 plain text, the only repeated words are the and you see them both repeated in each of those plain texts. So perhaps it's just the or and repeated there. I think we'll skip that idea about keyed row transposition. That doesn't really make any sense. One idea is that it's keyed columnar transposition at width 14. There's the AMSCO cipher, which you've got different block sizes. So an AMSCO cipher of width 14 actually has 21 letters in each row. Doesn't seem to help though. And then there's various ideas you could come up with based on the fact that 7 choose 2 is 21. But when we come up with these ideas, we start having to invent our own cipher types, which makes it rather difficult. So what I was saying was, what could be a sign that we unwound our first transposition correctly? And ideas that people have come up with, they say, well, look at this diagram down here. If we were to write K4 as 98 letters, or even 97, into a width 7 matrix, or we treat it as a keyed columnar transposition of width 14, we have almost all the Ks, 7 of the Ks in adjacent rows, which happens about 1% of the time. And as I was saying, you have these repeated doubled letters at width 7 as well, or width 14 if you want to consider it as a transposition. One optimistic way of assessing that is that you have, if we do random permutations of the K4 ciphertext, about 1 in 1750 permutations have at least 5 doubled letters in adjacent rows. On the other hand, I wouldn't take that at face value. I'd take it with a grain of salt because we didn't consider any of the other widths there. So maybe if you combine those ideas, you could start looking at non-Kryptos alphabets in your polyalphabetic substitution, since no one's found anything with these. Although I think I've looked at this and it hasn't unfortunately led anywhere. So if you took an obscure keyword, it has to be like Hoplo Cryacaras, however you pronounce it, an American fossil, you know, then you do get your 7 Ks in a row. I mean, it's American, it's ancient, it sort of fits in within the low of K4, but it's really obscure. And, you know, I've a joke about fossils. I've dug quite deeply into this, and it hasn't led anywhere. Getting back to that, what could be a sign that you've unwound the first transposition correctly? Well, with 12 column transposition, you need at least with 12 to get Kryptos in your output, and you've got KR, YP, SO, and T on the original Kryptos sculpture on the left-hand side and the right-hand side. So is this an idea that you do a columnar transposition or a root transposition? You don't see this pattern on Antipodes or the untitled Kryptos piece, and you won't be able to get Kryptos if you do a with 14 key transposition. So is the SO Bostrofeden, like, is it a hint that you're doing some weird root transposition? Is it a hint that it's some sort of digraphic cipher still involved there? I don't know. You know, wild speculation. If you see onion in there, if you drive the consonants out to one location, then you drive the vowels into another location, and then you're much more likely to see onion in there. I don't know. Another idea is that, as we've been looking at, do you see very high numbers of repeated n-grams in there? So if you were able to find a simple transposition, again, that word simple, and you got BQSZT repeated, then you'd have the same concept as you saw in K1 and K2. You'd say, oh, it's a fairly short ciphertext here, and we've got repeated 5 grams, and that's very unlikely to have happened by chance. We should proceed from here with our polyalphabetic ideas. In fact, the crib east-northeast, maybe that's a hint that it's a length 9 polyalphabetic, because you've got east lining up with east there. Okay, so another idea is that it's root transpositions. I don't know whether Americans would pronounce it route. Maybe I should be too, whatever. Now you see that in K3. We'll just discuss that in a moment. Now, as I was saying, the SO in there could be a hint of Bostrofeden transposition. It could make the first transposition very hard to find, and the width 21 statistics we're seeing are a hint at what direction to do. So I think they were outlined by Parker Hitt in 1916. So you probably find them in Sinkov or Gaines somewhere if you want to look. But here's the classic list of the 48 root transpositions from the cryptogram, Fiano or Jude Patterson. There's some mistakes in here, but it's not too hard to work out what they are. You pick the lengths of the rectangle sides, so not squares as you have here. You follow one of the 48 roots and you read it out again. And this is in line with the Sanborn comment that K4 is geometrically more difficult than the other ones. So maybe it's a hint towards root transpositions. Some ACA people really hate root transpositions. Trying to solve them manually with pencil and paper is a real pain, but it's a cinch with computers these days. I would say that onion is reminding me of these spiral or crab spiral transpositions on the right-hand side. In fact, K3 is just 2 of these root transpositions, these simple orthogonal ones applied sequentially. So it's when we saw the Sanborn worksheet, we could actually see it was number I think 6 or 7 applied twice. I should say it's number 7 applied twice if we start with the ciphertext, and it could be any number of rows on the side here, as long as we have the product of those rows equal to 192. So the actual choice after we saw Sanborn's worksheets was that it was root 7 and 24 in the first transposition and 8 in the second. So 24 8s are 192. So this brings up the possibility of incomplete root transpositions, which are a bit more complicated, perhaps with 7 and 3 rows in each rectangle. So on to the last 3 slides. Another idea, as I was saying, is to consider the width 21 as like blocks of 7, 3 apart. So can we do a transposition of width 14 and have the blocks 3 apart? So here's a nice multicolored diagram with all the blocks of 7 associated in different colors like that. So we can go 1, 2, 3, 4, 5, 6, 7 here. And then what this is equivalent to is transposition at width 14 with some interesting arrangements. So if we chose this arrangement, that's what we have here on the left-hand side. We have 14 repeated bigrams, 3 repeated 3grams, and 1 repeated quadgram. So this LSLW here. And comparing the K4 ciphertext to shuffles of itself, that happens about 1 in 89,000 times. Or we could do it this way, 1, 4, 2, 5, 3, 6, and then 7, 10. That's analogous to what I was looking at on the previous slide. You've got 16 repeated bigrams, 1 repeated trigram, and it's about 1 in 200,000 comparing K4 against shuffles of itself. So I guess this one is my response to Jim Galogli when he says there are some interesting patterns, but it could also just be coincidence. I would classify things like this as being still a relatively simple kind of transposition, but resulting in some very unlikely repeated n-gram counts here, but nobody knows what to do with it. Okay, these kinds of methods, that's transposition followed by polyalphabetic substitution, or possibly transposition followed by bigraphic substitution, because we've got so many bigrams. They do fit in with the concept of what we seem to be seeing with K4 is that you give away as much plain text as you like, or Sanborn reveals plain text, and nobody seems to get any further with the method. So if it was, if we knew that it was transposition followed by digraphic substitution, something simple like Playfair, that would help us a little bit, because we know that in Playfair, letters can't encode to themselves when you do Playfair encryption. And again, just one more quote from Frank Lewis, another cryptographer. When faced with solving a difficult cipher, don't just sit there and give it the crypto stare, you have to do something. The implication of that is that people have paralysis by analysis. They're spending too much time on twiddling, not doing things, so there is still a chance that it could be relatively simple. And again, this could all be entirely wrong, and it's entirely possible I missed something very simple here. When K4 is solved, as Jim Galogli says, it'll look obvious, like a magic trick. Some grounds for skepticism about what I've said are, Sanborn has said that K4 is a whole other ball game. It's, I think Scheidt or Sanborn has said it's something else. So would what I've been saying here really be all that different to K1 to 3? And also we have this quote that each was encrypted differently. which already isn't true when you look at K1 and 2, but it does make you wonder if something else is at play. But I think we have to keep the methods quite simple if we're going to have any sort of chance of getting an ordinary cryptographic solution.